Alright, this is a follow-up video to a previous video that I did on using Risa to implement the direct analysis method. So a viewer had a comment, and their comment was essentially whether or not I've tried this out with the latest version of Risa and the new method that they have to take into account P-delta effects. So what I did was recreate the models from start. Just go ahead and show nothing here and turn on some of our section sets. Actually, turn on the shape, and I recreated the exact same model that I had before of a W14 by 30 that's 12 feet long and is loaded to what I know to be kind of like the calibrated capacity of it as far as allowable strength design method is concerned, using the direct analysis method. So you could go back to those previous videos and see how the models are created, but what the users pointed out to me was that, of course I said I was using the previous version of Risa, and that version of Risa only had one particular, I guess, methodology of implementing P-delta. That information was found in this setting right here. If you have an old version of Risa, you will go to your model settings. In the newer version, you can click on this icon here. Oh, by the way, just to demonstrate, this is a latest and greatest Risa model as of April 2022. In fact, I just downloaded this model this morning. I was told by some of the guys at Risa that the new version was available. Go ahead and download it so I could check out some issues that I brought to their attention. So I'm just going to test this out first with our direct analysis method so I can address the viewer's comment. Alright, long story short, you come over here as far as P-delta settings are concerned, and in the solutions tab you go to advanced, and here we'll have our advanced options for P-delta settings. Everything else is pretty much similar to what I discussed in the previous video, with the exception of the biggest difference is probably this P-delta analysis option. So here it allows you to pick between using a standard nodal shear or a geometric nonlinear stiffness matrix. Now, Risa has help information that can explain to you the difference between the two, but the long and short of it is one uses more a manipulation of the forces, the shear forces from the previous model, which requires your elements to be broken up into a lot of parts. So it had to be broken into several different, joints, if you will, between the main top and bottom of whatever that element is, or the main supports of that element. Using the geometric stiffness matrix analysis allows you to basically include the stiffness reduction due to compressive load directly in your stiffness matrix analysis. So this is a more generic and direct way of doing this. By the way, this is the way SAP 2000 does it. This is the way, as far as I know, Robot does it, and I believe STAT also takes it into consideration just as well. I don't know if STAT has options, but I think geometric stiffness matrix is what they all modify. So that's important. And I'll demonstrate the difference between the two. The other thing that I noticed that Risa updated was their convergence tolerance. Because previously, out of the box, you're going to get a convergence tolerance of 0.5%. That's what it's going to have the default setting to. So if you don't pay attention to this convergence tolerance, you might not get the right answer. So in the previous videos, I had to make this convergence tolerance smaller and smaller in order so I could get a more correct analysis, if you will. Here, Risa has wisely limited the, I guess, the minuteness of this value right here. So now I can only go to 0.01%, which is very small, right? So if I try to go less than that, like, you know, whatever it is, when you click out of here from 0.0005%, it goes back to 0.1%. So this is the convergence tolerance that I would recommend that we use. But I ran some analysis and I see that it's also working very good, if you will, at 0.5%. So that's something to take into consideration. But that 0.5% was working well with the geometric stiffness analysis method, not the nodal shift, not the nodal shear analysis. So anyway, I'll just go ahead and run this thing first with nodal shear to demonstrate the difference between the two. Say OK to that. You can see my code. Everything is set 36010 AISC method. I am iterating on the stiffness adjustment. That's our tau sub b factor right now, even though I know I don't have to, but I just set it to be an iterative value if necessary. All right, everything else is as was before. I'll say OK to that. All right, I'll go ahead and display the loads that are on the structure. Like I said, a horizontal and vertical load added together, and I am running a PDELTA analysis on this, and you can see it from my load combination case that PDELTA is selected with that Y symbol there within the load combination table. So this load case number 1 L PDELTA includes that, and this will be the run with the nodal shear. Let me explain before I actually run it what I have in front of you. So the length of these elements, as I said before, this is a simple cantilever column, 12 feet long. All right, see 12 feet there, 12 feet there. You go to any one of them, you get the same thing. All right. Now you see I have certain nodes in the screen on the screen. This particular model that I have on the left side, the first one, I have it broken into 2 individual elements. All right, and that's just for analysis purposes in this case, but I will show you how that affects your design if you don't pay attention to the settings. If I can select this one, you'll see that's just 1 element versus these other 2, number 3 and number 4. They are physical elements, if you will, physical elements with nodes in between. I could select the node in between, or I could select the entire structure just by itself, and you'll see everything highlight versus having to break it into 2. All right, so this is the way that I recommend any structural engineer to model their structures, with adding nodes between their physical model. And the way that you would do that is basically using this command right here, add nodes, instead of split physical. Okay, so you would add nodes without splitting the model into pieces, because it just basically give you more work to do, more headaches, more problems. You don't want that. All right, so what we're after is just the correct analytical results. All right, that's the long and short of it. And now we run our analysis here. Check out our results. Okay, remember I'm using my nodal shear in this case. So here, if I take a look at what is my maximum bending moment at the base of the structure using nodal shear, I have, for the element, these 2 elements, you can see, excuse me, these 2 columns are analytically the same. The one that's broken into two individual pieces or the one that has an intermediate node. So the results are analytically the same. See, I think I could blow this up, but I have to zoom into it. The maximum moment at the base of this is 8.5 kip feet. Let's put it in kip inches for a second, just so I'm consistent with some of the other things I'll pull up. All right. Risa sort of has to recalculate when you swap units after running the analysis. So you just have to run it again. All right. But you can see these two numbers are the same, 101.6, 101.6. So analytically we have the same thing. However, the other column that's broken into four pieces instead of two has a higher moment value of 175.4. You right click, left click, and then right click on the element. I believe it may, or if I double click on it, might be able to pull up. So it doesn't do it like that, but we could take a look at the details of it by going to its actual detail analysis. And you can see the bending moment, shear force diagram, and all that good stuff. All right. So here we have it. And the bending moment about this weak axis is 175.4 kip inches. By the way, let me throw this thing in 3D so that it could be clear as to how the structure is loaded and bending. Put on my 3D. Go ahead and show some loads. You can see here that it's bending about its weak axis, and these two moment values are different. All right, so right off the bat, you know that making your model into more discrete points, if you will, or breaking it down to discrete points using nodal shear gives you different values. Okay, and the more you would break it up, the essentially more correct the analysis is. In this case, I think previously I would have to, using nodal shear, you have to break it into like something almost like, I believe it is 8 or 16 elements. It's a lot. All right, let's take a quick look at what's the effect doing it with geometric. Okay, so keep in mind our number before is the two numbers that we had were essentially 101.6 for the one that was broken into two, and the other one is 175.4 for the one that was broken into four. All right, as far as maximum bending moment at the base of the column. We'll change our PDELTA analysis method, say OK, and run the analysis again. Let's look at these values. Now I'll go ahead and put it in our X and Y plane, just for clarity. One thing you can notice right away is that the model that just has the number 2, this is the one in the middle, is different from, as far as the maximum bending moment, is, if you will, dramatically different from the ones that are broken into several different nodes. Let me go ahead and turn off our 3D view so you can see these nodes. All right. So even if you're using the geometric nonlinear stiffness method, it is still incorrect, if you will, or inaccurate, which is incorrect, all right, to only have um, two nodes between your element as far as a critical structure. Anything that you're going to rely on, any one of these things that are really like moment frames, you want to break it into at the minimum two pieces, all right, in order to get a more accurate bending moment from the analysis. The number one, even as it's broken into individuals, you can see number one matches number three. Exactly. It is the exact same thing as far as the analysis, and as far as the computer is concerned. All right. Only difference is when you do the design, and I'll show you about that. Number four and number three pretty much came up with the same, very similar values. This is 240, if you will, 239.2, and you could say 235.8. Is, if you were to be doing design, you probably want to round it up. But the even more accurate analysis, you could say, is when you break it into four. And I'm pretty sure we don't have to do it more than that. But just to demonstrate, I am going to copy this over and go from a 4-element model, if you will, to an 8-element model. All right. When you make modifications, that deletes the previous analysis, and I'll just go ahead and copy this over 5 feet. Now, the way that you can delete the nodes that were copied over, they're actually easy to delete. You just draw a window, highlight around it, and hit the delete button. They go away. Now this is back to just seeing one element, if you will, analytically. Go to add nodes, go from 4 to 8. I will apply it to my selected, and that's the only modification I'm going to make. Run the analysis. Take a look at my bending in the Y, and you can see essentially my 4-element model and my 8-element model have converged on 239. All right, so the same element, the same. You don't need to break it into all those pieces, but if you're one of those engineers that just is a little nervous about certain things, break it into at least 8 pieces. But I would say, to be honest with you, break it into at least 2 pieces, but be conservative. If it's a sensitive structure, a structure that you're concerned about, you might want to break it into 4. What does this mean for design? Well, let's check out our design ratios, because all of these unity checks will be giving us probably some different values. Okay, come over here, take a look at our stress ratios. The 2-element model matches what we have over here, with the exception of it broken into different pieces. Now let me show you, if you end up somehow breaking your element into different individual pieces, by default it's going to have whatever the length is between the nodes. So you have to actually go into the design property section and modify that length to reflect what it actually is. All right, so I'll delete all of this real quick just so you can see. Let's see here, go here, delete all of that. Yes, go ahead and make modifications. I believe if I just hit delete, it'll go to its defaults. We'll see what happens. All right, run the analysis. Take a look at the design stress ratios. You see, Now this went back to its default length. When I select it, if I check design out, this element that wasn't working at 12 feet is now working in this condition. So again, you have to pay attention to these things as a structural engineer. Don't just have garbage come in and have garbage go out. See, the length in this location is listed as 6 feet, and that's the length between the nodes. All right, so garbage in, garbage out. Here, this is the more accurate design. It has the correct length, and that length, of course, affects its axial capacity. So that's why it's, has different stress ratios. You can see the length is 12 feet here, and it will have a different axial capacity if you go through your analysis and check that out. Okay, so the great thing about Risa is that it gives you all of the calculations in detail, so you can investigate how it's coming up with its numbers. All right, so one last thing, I'm going to actually show something that does work, and then we'll pop up SAP 2000 to make a comparison as far as the just a quick look and make sure it's the same thing, but I've checked it 100 times and it is the same thing. Now let's go ahead and copy this over, and let's put up a column that does work. So I'm going to keep it at the discretization, the part that has essentially the most of the internal nodes and internal elements. Come over here and say to myself that I will change this element into a better column section, and I'll just use the column section that I would recommend for real building design, which would be a W14 by 43. Look at some other videos where I discuss this, and basically you want to pick a column. When it comes to columns, you want something that's square. So a 14 by 43 is it? Let me look at this, make sure that I'm right before I make a mistake here. But you want to pick a section that has more beef to it. All right. So as far as column sizes, you might want to start with it's not square, but it's approaching something that's more square. But column sizes, the column size might start at a 14 by 43. That'll be something better than a 14 by 30. You see the width of this flange is 8 inches, so 14 by 30 has a 6.7, almost 7 inches. So it's similar, but believe me, an inch makes a difference when you're actually talking about detailing. So let's use this 14 by 43. Say okay. Everything else being equal, run the analysis. And go ahead and pull up our, of course we already discussed the bending and all that stuff. That's not going to be any good new information, so I'll check the unity here. Now I have a column that's 13% stress. Is something that works very well. You might want to use this column for this section if you had these loads on it. All right, let's take a look at what SAP had said for this same structure. I have it pulled up easily. Let's say here, voila. Did the same thing. Sorry. Zoom in. over here, turn off my analysis model. I was only showing my analysis model to show that I broke it up into several pieces. You see I have 1, 2, 3, 4, 5, 6, 7, 8. So 8. Let's turn that, actually I'll leave it on for a second and just turn on my sections and apply. This one is a 16 by 40. This one is a 14 by 43, also 8. Load wise, go here so you can see that I have the loading on the structure. I go to the loads tabs, that's the loads. You can go to my SAP 2000 to see how these models were created. Go to my SAP 2000 video. But it's loaded, and go ahead and run a design on it. And I'll show you something interesting about SAP just as well. When you take a look at our design ratios, everything else is the same. You'll see the one that was the 14 by 43 has a design ratio of 0.09, so about 10%, instead of 13% like Risa was telling us. Reason why that is because SAP 2000 actually do not, or at least as far as I know, they don't do an accurate check on the axial capacity. So this is something that I need to write to SAP about, basically. And what I mean by that is that when you select the member, click on it, right click while you're in the design phase, go to the controlling section. It will be the one that's already highlighted by default, and click into the details. You know, SAP is using this moment interaction check for its analysis. You can see that here also in this area. And this is sort of like what SAP is focusing on, combined bending. Well, this value might be smaller in the end than straight axial load as far as the required load over the given capacity. So here you'll see our required load is 33.12. Take that number and divide it out by our capacity for compression. That's 247.213, and you'll see that you end up with 13%. Now I'll do that on the video. Let me see if I can find my calculator real quick. Maybe moving things around a lot, but here I bring up the calculator app. So coming over here and just saying what the axial load is, the PR 33.215. Let's divide that PR by its axial capacity, which is, so divided by 247.213. 247.213. That's 13%. Last time I checked, 13% was greater than 0.096, and that's why this should be the controlling value. Guess who gets this? Guess who gets this information right? Risa 3D does, as well as some of the other software that I've used. That's why we have this 13% capacity. Okay, so all right, that's the long and short of it. Please make a comment, subscribe, like, dislike, do whatever you want. But basically, if you give me feedback if you're interested in these type of topics, and I will, respond to the comments. Also, anything else that you want to have on our channel you're interested on, and just go ahead and give me some feedback, and I'll see what I can do for you. All right, peace.